Okay, so our next and final unit for this semester is not as short as our last one, but it's still pretty short. It only has 4 sections. We will be able to have a test on this the day before your final exam. Sorry about that, it's just the way it worked out. We'll see how this unit goes. Obviously, I'm willing to be kind of flexible. We need to cut out a section or something of that nature. But really, we're going to be working with quadratic functions. So we've studied before how to solve quadratics. Now we're going to look at things like, how do we graph them? How can we model with them? How can I solve a system that now has a quadratic and a linear function? So this is a good unit to have right before your final, because we're going to touch upon a lot of little different things about quadratics in this here. So we're going to be able to graph parabolas in standard form. As a warm-up, I don't think you guys have anything in there, right? Because when I printed these, I wasn't sure. Go ahead and write this down as our warm-up question. What is another term used for x-intercepts of a quadratic function? What's the answer to that question?
Zeros.
Zeros, right? Just to kind of bring us back, zeros. Anybody know of a different one? Remember? They are also sometimes called roots, or even sometimes called solutions. But the one that we want to remember is whatever word the ACT or your textbook or whatever, once you go out into the great wide world after high school, whatever they're calling them, they're really just x-intercepts. So as we start to graph these, remember, these are the solutions to some of the things that we solved back in Unit 2. Just instead of us solving them algebraically, we're going to find them on the graph. And we're going to use some shortcuts to figure out what those are. So let's talk about what is standard form of a quadratic function. Let's formally put it in our notes. It is ax squared plus bx plus c. And the graph forms our shape, right? And we've used this term for a while, which is a parabola. It has a U shape, either up or down. And I know on the discovery activity you were just doing, right, I was having you use the table that Desmos created. But remember, you can always just algebraically, if I plug in -2 into this function, what's -2, the quantity squared? +4, right? These are just giving you different values that are solutions to our function. And then we can go ahead and graph them. So our parent function is just x squared, right? It's got nothing applied to it. I haven't moved it left, right, up, or down. This is the function that we then transform and move around the coordinate plane. What is the vertex of this function, of our parent?
0,
0, 0, the origin, however you want to write it, right? Our vertex, we kind of start off right centered around the origin. Now, what is the equation of our axis of symmetry? Yep.
X equals 0.
X equals 0. So our axis of symmetry is always going to cut our parabola in half, and it's always going to be a vertical line. Vertical lines, right, start with x equals followed by a number. So when you start filling these things out, know that we're looking for an equation of a line. So I need to see x equals in there so that if I were to put it in Desmos, it would graph me a line. So let's look at a couple of other functions, and it's very similar to probably, similar kind of to the ones that you did in that discovery. I just want to see, okay, what happens if I put a 2 out in front of my x squared? How does that change the shape of my parabola? So first, let's fill out our table. So if I do -2 squared, remember as I do this, I have to follow my order of operations, which I get this question all the time. I have to do the exponent before I multiply, right? So I get negative 2, the quantity squared 4, 4 times 2, 8. Negative 1, the quantity squared 1 times 2, 2. Let's go ahead and plot these points. So what I already have plotted on here is our standard x squared. And we're going to add our new function, 2x squared, over top of it. So how does this compare, right? We started with our parent function, the black one, and now we're at the blue one. How is it different?
It's more narrow.
It's more narrow. That's exactly what I'm looking for. And really, the reason why it is narrower, this 2 out in front works the same way we saw transformations in our last unit. We're stretching it away from the x-axis. But I like your description of narrower, because that's how I'm going to make you describe it later. Is it narrower or wider than our parent function? All right, let's look at our next example. Now, I have just x squared, but I tacked on a plus 3 at the end. So let's calculate this. If I plug in, right, negative 2, the quantity squared plus 3, I get 4, and then I add 3. 7. 1, and then I add 3. Now, how does this one compare to our original? What did we do here? We changed our y-intercept, right? We shifted it up, which I'll use our fancy term. We translated up 3 units. So now our y-intercept is not at 0, 0, it's at 0, 3. And it's kind of hard to see with this graph, but this graph is not narrower or wider than the original. It has the exact same shape. All that we've done is translated it up. Questions? I think pretty straightforward, right, with all the work we've done. So this whole section is all about, okay, how can we use some of our algebraic understanding about quadratic functions and everything we've learned about transformations so far to just be able to look at a function and determine some things about it. So we're going to fill out this table, which I hope that everybody will be able to refer to as they go through and kind of graph some of these functions. So I'm going to rewrite down our standard form. And a couple of these things, right, we already discovered as we went through the whole process. The graph is going to open up or have kind of a regular U shape if A is positive. Or I wrote A is greater than 0, but feel free to write A is positive, whatever makes the most sense for your notes. And then it's going to open down if A is negative. We saw that in the discovery activity. Now, in this example over here, right, it was narrower when I had an A value out in front that was larger than the number 1. So the way we're going to write it is if the absolute value of A, because it could be negative or positive, is greater than 1. And it's going to be wider, it's going to be kind of a fat parabola if we end up with a fraction. If the absolute value of A is less than 1. So something like 1/4. That's going to give you a nice fat kind of parabola shape. Now here's the big one, right? Here's the one where we really need to kind of be told this one. This is not one that we necessarily discovered. My axis of symmetry is that equation, negative b divided by 2 times a. And I recommend that you memorize this, because if you continue on with math, pre-calc, calculus, all that stuff, they're always going to give you quadratics in standard form, which is everybody's least favorite form because it doesn't tell you too much about it. But if you can kind of remember to do that negative b divided by 2a, you're going to know where your vertex is all the time. So it is worth memorizing. Now, in order to find the vertex, we know the vertex exists on this axis of symmetry. It's somewhere on that line. So what you do is you plug in x from here to find the coordinate plane. So you take this x value that you have here, and you plug it in to your original equation that you have been given. And when you do that, right, you're calculating f of a number, f of 2, f of 3. And that is going to spit out the coordinate point that you need to determine where the vertex is. Our next one, the y-intercept is c. So the point 0, c is on our parabola, right? And that's going to tell us if we've translated up or down. And then our domain and range. Anybody want to tell me what the domain of a parabola is? What can I plug in for x? Anything. So your domain is always going to be negative to positive infinity, just like our absolute value functions. Now the range, that's different, right? It doesn't go as low or as high on the y-axis. It depends. So your range is either going to be your y value from your vertex up to positive infinity, or from negative infinity up to the y value of your vertex. And I'll write that. Right? Because your vertex is going to determine if you're a minimum or a maximum. Yep?
If the minimum was like 3, could you also say y is greater than 3?
Yes, you can write it that way, absolutely.
Or greater than or equal to.
You do not have to use the interval notation that I always use. You can definitely use inequalities if you want.
All right.
Yep. And I will say, after teaching pre-calc, predominantly you will see it this way. Like, for some reason, they really love interval notation. But then I also think ACT prefers inequality notation. So being able to know the difference is why we studied it for so long. Questions on this table, because we're going to use this table. Now there are 4 examples in your notes of us graphing. I'll do as many as you guys feel like you need to be able to get a hold of this. But I think we'll just keep referring to this table, and hopefully not our graphing calculators, but if we need to use our graphing calculators to help us along the way, we can do that. So let's look at letter A below of part of 2. So does this quadratic open up or down? Down. Right? It has a negative that's in front of the x squared, so I know right away I'm going to get it's going to be upside down. So if it's downward facing, does it have a maximum or a minimum?
Maximum.
A maximum. Now for my axis of symmetry, here's where we're going to start to do a little bit of work. I've got negative x squared plus 6x minus 8. So my a is negative 1, my b is 6, my c is negative 8. In order to find, and this is just like the quadratic, right? Everybody see we're still using a, b, and c just like we did with the quadratic formula. If I want to find my axis of symmetry, I do negative b divided by 2 times a. So negative b divided by 2 times a. So I get negative 6 over negative 2. I get x equal to 3 is my axis of symmetry. And the first thing I like to do when I'm graphing these is I graph that line, and I make it a dotted line. So x equal to 3 is right here. I'm not entirely sure where my parabola is yet, but we'll put it there. Now to figure out the y coordinate of my vertex, I'm going to plug in x is equal to 3 in here to find it. So if x is equal to 3, what is y? Well, let's plug it in. And yes, you can definitely use your calculators to help you out. I don't want anybody making arithmetic mistakes. Remember, this one here always gets everybody. I apply the exponent before the negative. So therefore, my vertex is at the point 3, 1. So I go ahead and plot that. Y-intercept. Well, for my y-intercept, right, I just look at my c value. My c value tells me right away that my y-intercept is at 0, -8. And I plot that. Now the question becomes, in order to graph a line, remember back in Unit 1, I only needed 2 points to graph a line. In order to graph a parabola, you need 3 points. And the way that we're going to find our third point is because parabolas are symmetric, I'm going to take this point and reflect it across my axis of symmetry, right? So if this point is 3 units away from my axis of symmetry, I just go 3 units further, and I have my third point. And then I connect the dots, draw my parabola to the best of my abilities. Doesn't have to be perfect. At least once it's graphed, it's going to be easier to figure out domain and range. Yep.
How did we find the y-intercept?
It's just the c value.
Oh, okay.
And another way to think of it, okay, let's think of it this way. Y-intercept, what's my x value for a y-intercept?
0.
So I just plug in 0 into this formula, and I'm always going to get out the c value because there's no x attached to it. Okay? Now, is it narrower or wider than my original parent function? Or the same? It's the same. If you don't have, if this value here is not a 1 or a -1, then it becomes wider or narrower. When when the absolute value of A is equal to 1, it's going to be the same in terms of narrower, wider shape, basically. My domain, right, the domain always goes from negative to positive, infinity. And then my range goes from -infinity all the way up to 1. And I include the 1, so I put the little bracket on there. Questions on that at all? Because with all the work we've done in all of our previous units, right, filling this stuff out, hopefully not as hard as it would have been if this was like our first unit. You want to try the next one on your own? Yeah? Go ahead. Give the next one on your own a try. I will kind of eventually start adding this information down, but try it on your own first. That's a good idea. That's a good idea. I like that.
So like this or like on this part, I can only do that, but at least you can say at least do something, right?
That's a good strategy.
Okay. I'll try to remember that.
Okay. This one's much steeper. All right. So I see a positive in front of the x squared, so I know it's going to open up. Therefore, if it opens up, it has a minimum value. It's not going to have a maximum. For my axis of symmetry, I have my a, b, and c, so I do negative b divided by 2a, which gives me negative 6 over positive 6, which we simplify, right, to negative 1. So x equals negative 1 is my axis of symmetry. Then I plug in negative 1 to find my actual vertex point, so it's negative 1, 0. That 3 out front tells me that it's going to be narrower, definitely much narrower, right? I guess we could have fit a 4th and 5th point up here, based on the graph that we had there. So it's narrower, my domain, negative to positive infinity, and then my range, we go from 0 all the way up to positive infinity. How are we feeling on this? Not too shabby? Do you want to do another example, or are you feeling okay? Up to you guys. C has a fraction in it. Do it or not do it?
Do it.
Do it. All right, let's do letter C. So go ahead, get started on that. Don't worry about the whole fraction thing out front, although it will dictate that our parabola is going to be wider or a little bit fatter than kind of our standard parabola. But take your time. So many negatives in this one. Or 5 halves, however you want to write this. Plot that vertex to the best of your ability, because it is in between the grid lines. actually graphed my parabola yet. It's pretty tight. Would we all agree? Like, what's it going to look like after this? So here's what might happen, especially as you're doing the homework assignment. If you have kind of this U shape, you're like, well, I know it should be wider because I know what the A value is, and it's less, the absolute value of it is less than 1, so it's going to be a little bit wider, but I'm just not sure how to graph it. I highly recommend that you find another point to be able to, right? Because this whole section, this section and next section, is all about graphing quadratic functions. So I am going to be a little bit precise, or I want you guys to be as precise as you possibly can since that's our learning target. So how can we find some additional points? I could just plug in some numbers, right? The other option, let's all make sure, because I know we practice on Desmos, but let's make sure we remember how to do this on our calculator as well. Let's see, I've got mine open, so let me go over there. Oh, come on, I was just in here. Yes, I realize my batteries are low. All right, so let's remember we know how to type this into our calculator. Go to your y equals menu. Hopefully there's nothing in there. If there is, clear it out. And we're going to type in -1/2. So I'm going to type it in exactly as it looks. You can definitely put in 0.5. If you would prefer to put in 0.5, you can. Followed by our x squared minus x plus 2. And then we'll look at the graph, make sure it looks right. Yes, it looks like what we expect it to. So here's where I recommend, right? If this is the goal, to be able to graph this, let's go to our second graph and see a table of values, because maybe there's a value on there that is, in my opinion, right, easy to graph. So I see one, there's -4, -2. That's going to be right on the grid lines, which tells me that I've got another one at 0, 2, or sorry, at 2, -2. So there's a couple extra points that I can put on my graph that is going to make it easier for me to graph it. So I've got 2, -2, and -4, -2. And honestly, right, the better we are with our calculators and the more comfortable we are with using them, easier it's going to be on an ACT. The more you're going to be able to use that as a resource. Anybody need a hand? Did you need a hand, Carter? Something that typed in.
I put negative.
Oh, that's not the negative button. That's the minus sign. Here, now graph it.
All right. Yeah. All right. Thank you.
I know. And that's why, right? You're not gonna have Desmos on the test. So let's make sure we know how to use our graphing calculator as help there. So it opens down, has a maximum, our axis of symmetry, and our vertex we find by plugging in our points, our y-intercept. It will end up being a wider function than our parent. And then we have our domain and range to kind of finish it out. That was good. We at least did a fractional one. Those are always the trickier ones. Questions? Yes, second graph, I know. It comes in handy. The more we use them, the easier these become. All right, let's skip over letter D. If you would like it, though, my answers are on Google Classroom. I've uploaded all my notes for this unit so far. Let's get into our word problem of the day. Who here has been to San Francisco and gone over the Golden Gate Bridge? No? Just one? All right. I'll take it. Pretty cool bridge. It's a bridge. It's a cable bridge, right? So it has this familiar shape, which hopefully we've at least seen it now that like Full House is back program, right? People have seen this kind of shape before. Each cable joining the two towers of the Golden Gate Bridge can be modeled by this particular function, right? Models in real life don't have nice whole number setups for all of our coefficients, so that's what we have there, where x and y are measured in feet. What is the height h above the road of a cable at its lowest point. So say we're walking across the Golden Gate Bridge and we see the cables. Can Miss Sedlick jump up and touch the bottom? Will it get that low? I don't know. Let's figure it out. So if we have this function, notice it's going to be a pretty fat parabola, right? Look at our a value. So it's got this kind of shape. It's going to open up, right, as it looks right here on our picture. How do I figure out my vertex here? How do I figure out the x and y coordinate there? How have we done it on the previous examples? Carter?
You take 7/15
Yep.
divided by 2 times 1 over 9,000.
We're going to do that, but with some pretty ugly numbers. We're going to find basically the x value, which will tell us how far do I have to walk across the bridge, right, to reach the lowest value. That's the horizontal. And then the y will tell us how far or how high up that bridge is at that point. So we have negative 7/15 divided by 2 times. Do you think we can do this without our calculator?
No.
No.
Nope.
Yes, you can use your calculator, but hopefully you get out 2100 as your answer.
How do you put something in a fraction?
Divided by sign. We'll give you the divided by part. Or you could do it out by hand. So I multiply my denominator. That's 7/15 divided by. So when we divide fractions, we multiply by the reciprocal. So let's see, is this in feet? So I've got to walk 2,100 feet across the bridge to get to the lowest point. Now let's see how high up that cable is. So I'm going to take this 2,100 and plug it in for x. I might use my calculator on this one. So I don't know. You think Miss Sedlick can jump that high and touch it? I don't know what everybody's vertical is in here, but it's 10 feet off the ground. Definitely a bit lower. I should have had us guess about how low we thought it would get. So, any questions though on plugging this in into your calculator? Yeah?
I somehow got 989.
Oh, you forgot to multiply by 2,100. That's fine. I know sometimes calculators are our friends, sometimes they're not. When it comes to word problems, we'll probably have to rely on our calculators. But yes, we can make mistakes.